Okay, the lecture today is going to be about the substitution method. For evaluating integrals. To motivate this topic, let me take you back to chain rule. Substitution method is really idea of a chain rule applied to integration. What did chain rule say? Suppose you have a function f of x, say x cubed plus x plus 1 to power of say, 5. You can really break this function into two functions. One is this so-called interior function, x cubed plus x plus 1, and then there is the other exterior function, which is taking this and raising it to power of 5. How would you differentiate this? Chain rule would say that to differentiate, take this item as a separate item, perhaps call it some other by some other name such as G or U or something, and differentiate that one. So that's going to be 3x squared plus 1. That's a derivative of the inside. Now that quantity raised to the power of 5, that's going to be your other function that you differentiate in the normal style of bringing the exponent up front, taking the base and raising it to 1 less than the old exponent. So if I had defined u to be x cubed plus x plus 1, then my f of x would have been just u to the power of 5. If I want to find f prime, I would say the derivative is 5 u to the power of 4. So I'm differentiating this thing with respect to u. Then I multiply by the derivative of u with respect to x. So u played the role of the substitution for us in differentiation here. Now exact same set of ideas can be applied to the integration, and the idea of substitution is used to keep track of all the little calculations we need to do. Let's just start with an example like this one. Suppose I have 3x squared plus 1 times x cubed plus x plus 1 raised to the power of 4 dx. Say I want to calculate this indefinite integral. Well, we have the advantage of having seen what function is it that gives rise to something looking like it. Almost the same thing is here except for that 5. So we kind of know what the answer is. That's not a bad thing that for the first time around we are looking at that. We want to see how do we go and do the bookkeeping so that our antiderivative will come out correctly. Here is how we approach it. We have to detect here presence of some function whose derivative is multiplying the whole expression that we have. Well, in this case it would be just this, and then we are going to take that as our substitution u. So I'm going to go ahead, change the language of this integration to language in terms of u. It starts by taking u as x cubed plus x plus 1. We go ahead and write the derivative of u. We typically would have used the notation u prime, but it's better to go to more professional notation, du dx. This is 3x squared plus 1. Now I remember our idea is to separate u's and x's. We go ahead and write this in this fashion. Now we are ready for doing complete translation. Let's go ahead and see what does it look like on the right hand side. So this is called u. So that is going to be u to the power of 4. What else is left? What else is left is this portion and then this portion. That is what is left. 3x squared plus 1 dx. Fortunately I have it here. 3x squared plus 1 dx is just same as du. So I just translate that to du. I go ahead and perform this indefinite integral. Remember, this means what's a function whose derivative will be u to the power of 4. Of course, it's u to the power of 5 over 5 plus a constant. Now the last step, we talk about it like this. The original problem was posed in the language of x. The final answer has to be in the same language. It's preferred that way. So we go and do a back substitution. Instead of u, I put back whatever I had here, x cubed plus x plus 1 to the power of 5. Then I had to divide by 5 and get a constant. So the function whose derivative will be that is given by this. Now let's go ahead and learn this topic by doing several examples. Here is one example. Suppose I ask you find antiderivative of 5x plus 3 dx. Well, I would have had an easier time with this if I just had an x in a radical. I would have applied the power rule there and get my antiderivative. But this 5 and 3 kind of throw me off. To cure that situation, I go ahead and rename this. I take that as my substitution. I take u to be 5x plus 3. Compress all of that into one variable. Then I go ahead for doing a full translation, getting rid of my dx's. Go ahead, take a derivative of this. A derivative here is simple, it's just 5. I go ahead and rewrite this thing and prepare it for future use. Now I go and say this radical simply is replaced by radical u. Well, I have to translate dx as well. How do I translate dx? You have to come to your equation here, the one with the differential, and see how can you use that to translate. Well, of course, dx is just du over 5. So I write it here, du over 5. Constant multiples could be placed outside. Radical u, I can write it as u to the power of a half. How do I integrate that? Well, we had the rule, you increase the exponent by 1, get 3 halves, divide by that is 3 halves plus a constant. Now I take 3 half, take the inverse of it and multiply by this. That's going to give me 2/15. U itself was this quantity, 5x plus 3. Take that and raise it to power of 3 halves, and then I am done. So really what you did for me here was to keep track of all of these constants, additional material, so that I get this constant of 215 without much problem. Let's go ahead and do another example. Suppose I say find integral of say 2 plus x squared times x to power of 5 dx. Obviously this integral doesn't show up in our table, and one has to find some roundabout way of making it act like one of those functions we have seen. Our first line of defense is just the substitution method. What is it that is to be substituted? Well, it's very hard to say in general what should be substituted, but remember that you're looking for an expression that something about its derivative is present. Typical rules of thumb is functions that appear under radicals, in denominators, in parentheses, in exponents and such are the first guess for us. So we go ahead and follow that advice. I take that as my substitution. I take u to be 2 plus x squared. By now we learned the drill. Du dx is 2x. So du is 2x dx. Now let's see if we can do our translation easily. This portion is easy enough. That is just radical u. We are stuck with the following: how to handle x to power of 5 dx. And this is one standard trick. X to the power of 5 dx, we have to bring somehow dx from here. Dx is connected to an x. And then for the remaining powers, we have to go to our original substitution. So I take x to the power of 5 dx and write it as x to the power of 4 times x dx. What was the reason for that? Well, x and dx were kind of conjoined twins here. I have to have them together. So I'll have an x dx. I have an x to the power of 4. What am I going to do with that? Here is what I will do with that. Here, this tells me that x squared is u minus 2. So x to the power of 4 is u minus 2 squared. So where are we right now? X to the power of 4, this portion gets substituted by this formula. That's u minus 2 squared. X dx, well, that is half of this, which is half of that. So that's going to be du over 2. Okay, so once again, this radical, that substitution was easy. This portion gave us a hard time. Run for the money. I had to split it into 2 pieces. One piece was available for me here. That was easy, du over 2. The other piece, x to the power of 4, I still had to go through the maze a little bit. X squared had to be extracted from here, and I need the x to the power of 4, so I take that squared. So here is the remain portion of this thing is u minus 2 squared, and then du over 2. Now let's go ahead and do that integral. That integral says radical u times u minus 2 squared du over 2. I do 2 things here, or maybe 3 things. I put the 2 outside. Radical, I write it in the fractional exponent. Open that, u squared minus 2u, minus 4u plus 4 du. Next step, I just carry out the multiplication. U to the power of half times u squared is u to the power of 5 halves times u minus 4u to the power of 3 halves times just a 4, it's 4u to the power of a half. The whole thing is du. Now we are home. We just take an antiderivative by raising the exponent one notch, dividing by that. This is u 3 halves becomes 5 halves. I have to divide by 5 halves. 1 half becomes 3 halves, and then I have to divide by that. I had the factor of 1 half in front of all of them, and I throw in my constant. Now I have to clean up. This 2 gets rid of the 2's in the denominators. Instead of u, I have to go back and do the substitution. U was 2 plus x squared. So I come back here. So this is 2 plus x squared to the power of 7 halves divided by 7. There is a factor of 4/5 in front. 2 plus x squared raised to the power of 5 halves. And here I have a factor of 4/3. And my u is 2 plus x squared to the power of 3 halves, and then a constant just thrown in. Then we are done. So you want to go ahead and practice this. Let's go ahead, apply all of this to some definite integrals as well, using substitution with definite integrals. For example, say, to go an easy example, let's say the very first problem that we handled here. What if I had limits for my integral which would have made it to be a definite integral? That's not really a major challenge. If you have numbers here, you have to calculate the definite integral. You just apply those numbers to this answer and subtract the two quantities from each other. So that's one way of handling the case of definite integrals. Let me go ahead and just pick an example from text with some more friendly numbers. Suppose the question is find integral from 0 to 4 of radical 2x plus 1 dx. Style number 1. Ignore the 0 and 4. Just go ahead and find the antiderivative or the integral, the indefinite integral. How would you do that? We know the drill now. This is 2x plus 1. Du is 2 dx. That becomes radical u. Instead of dx from here, I find out that the dx is du over 2. This is du over 2. Rewrite as 1/2 integral u to the power of a half du. It's 1/2 of u to the power of 3 halves over 3 halves plus a constant. That is again 1/2. So these are side calculations here. Let me put them to the side. 2 and 2 cancel. That makes 1/3. U was 2x plus 1, so I write 2x plus 1 to the power of 3 halves, and then a constant. So how did we calculate the definite integrals? We took the antiderivative, applied 0 and 4 to it, and subtracted. So here's one way I could do it. let me write it here, integral 0 to 4 of 2x plus 1 dx. I just write this 1/3 of 2x plus 1 to the power of 3/2. Just plug 0 and 4 in it. So 1/3 of, if you plug 4 in this, you get 9 to the power of 3/2. If you plug 0 in it, you get 1/3 of, luckily it's just 1 to the power of 3/2. Now what's 9 to the power of 3/2? Take the square root of 9, that's 3, cube that 27, divide by 3, then it becomes just 9. The other one is just 1/3. Take a common denominator, you get 26/3. Style number 2. Sometimes people prefer to do it like this. Let's start again. Same problem. Radical 2x plus 1 from 0 to 4 dx. Same as before. We take u to be 2x plus 1. du is equal to 2 dx. Now I substitute. Instead of that, I have radical u. Instead of dx, I had du over 2. The thing that is new here is that the limits also get substituted. That is, if x is 0, u becomes 1. If x is 4, u becomes 9. So if you want to do complete translation, you can go from 0, 4 to 1, 9. And from now on, you don't need to do any back substitution. You just keep going. So you go ahead and say this is u to the power of 1/2. We haven't integrated yet. I just rewriting it. Rewrite 1/2. U to the power of 1/2 is u to the power of 3/2 divided by 3/2. We don't need a constant. One half, these 2's cancel out, this 2 and that 2 cancel out. I'll have 1/3 u to power of 3/2, in which I'm substituting 1 and 9. Now this becomes 1/3 of 9 to the power of 3/2 minus 1/3 of 1 to the power of 3/2. By now you realize just same as what we had last time. This is your 9 and this is 1/3, and the answer as just the last time becomes 26/3. So it's a matter of style, which one of these two you prefer, and you just can carry it out that way. This fashion looks a little bit cleaner with the complete translation. Not only your x's and your formula, but also your limits of the integration are translated, and then you get the answer that way. Now this section here gives you the biggest challenge in terms of amount of exercises, really lots of drills and a wide variety of functions. Everything you have learned in terms of all those formulas you have seen from the beginning of calculus to now, all the differentiation formulas you have seen, everything comes in here. So it's a very good section for recapping calculus 1. Please go ahead and do as many of these exercises as you can. If you have any questions, please let me know. Good luck and God bless.